Now we want to talk about damped harmonic motion. So far we have been assuming that there's no friction involved. And what friction does is it's going to eat up energy. So energy is in any natural system, energy is always going to be escaping the system. So the system is going to start to lose energy. And that's going to be caused by friction. So let's first assume that there is no friction. What would it look like? And so let's look at an oscillator. And so this could be a pendulum once again. So you got a string of length L and then an M on the end of it. You're going to pull it back and you're going to let it go. And so it's going to swing down through the equilibrium point. So that's going to be down here. So the distance from here to here is again going to be L. I know it doesn't look like it, but so whatever this length is here, when it swings down to here, it's going to have that same length. Now when it gets down to here, it's going to have energy. So it has energy when it's up here. The kind of energy it has up here is called potential energy. Later we'll talk more about what I mean by that, but for right now it's so this is stored energy in the form of potential energy. Then when it swings down to here, it's moving, so it has kinetic energy, another kind of energy. And then since it's moving, it keeps going, and so it's going to swing up to here. So again, this is the same length L, and here is now. And so it's going to swing back and forth like this forever. So if there was no friction, then this thing would swing back and forth forever like that. Now let's make a graph of what that would look like. And so over here we could have the amplitude, and now this is going to be the equilibrium point. And so let's first pull it out here so that it begins with some kind of an angle. So here's the angle right here, and so it has a maximum angle when I first begin. And so let's say that that represents right there. So that's where I click my stopwatch, and I click it at the same time that I let the mass go. And so it's going to oscillate back and forth. So what would that look like? Well, at first the oscillator is going to be over here, but then it's going to be here. So when it's here, let's say it took 10 seconds for that to happen. That's a very long oscillation. But let's just say that it's now here at the end of 10 seconds. Okay, then it starts to go over to here, and so now it's going to be down here. Okay, but then it starts to swing back to go back over to here. So it's going to go through the equilibrium point again, and then it's going to go back up to here. So if we were to graph this, it would be going down like that, and then up like this, and then up like that, and then it would continue. So let's go ahead and continue this thing down, and then going back up again. Okay, so that if we were to graph the amplitude, how far out are we pulling this thing, versus time t, so this is the time is going sideways, we would get a graph like this. And notice that it's at its maximum, and then up here it's at its maximum. So notice that it's not changing. The wave is not changing. Now, let's actually include the effects of friction and then see what would happen. So in this case, we're going to have somebody in a swing, and they get going in the swing, and then they stop pumping their legs, and then they just slow down. And so what you find is that the amplitude starts getting smaller and smaller and smaller until finally they come to a stop. So what would that look like? So The blue is going to be this one. But then superimposed on it is a red color. So notice it starts out exactly the same place here, and it still goes through the midpoint. But what we're going to find is that the amplitude, each time that it does it, is going to be, so when it gets down to here, instead of going all the way down to here, it goes to there. So it has a slightly smaller amplitude. So that means that instead of swinging all the way out to here, maybe they're swinging out to right there. Okay, and then it's still going to go back through 0, but it's going to be, maybe it's now here. And then it's still going to go through 0, but now maybe it's right here. So do you notice that the amplitude is getting smaller and smaller? Now, what did we say the amplitude was proportional to? The amplitude is proportional to the energy. So the energy of the system is getting smaller and smaller. But energy has to be conserved. You can't create or destroy energy. So where's the energy going? It's escaping. It's being turned into heat. And so in the case of the person there in the swing, it's wind resistance. So as they're going back and forth, the wind is blowing against them, so you're getting air resistance. And so that is what's causing energy to escape. Now there's also a little bit of heat right up here where the rope is attached to the tree. There's going to be friction there, so it's also going to lose a little bit of energy up there. But most of it is going to be due to wind resistance. So when an oscillator moves through air or water, its amplitude gets smaller and smaller because it's losing energy. And we say that the system is being damped when that happens. So for purposes of the exam, just know what damped harmonic motion is, what does it look like, and then what is causing it. So make sure and know that for the exam. Okay, let's take a break, and when we come back, we're going to talk about forced harmonic motion and resonance.